I think this is more of an entertaining talk because I don't do neuromorphic computing, neither with hardware nor with software, except for the wonderful CSAs and exploring how they can be built into online learning and Bayesian optimization. Treat it as an entertainment talk. I will talk about the ingredients for efficient robot learning, and I will connect it eventually to this community by basically motivating why we need energy efficiency in robotics. So it's not going to be as, let's say, dire need for energy efficiency as what, for example, Amanda Prorok, who spoke here a day ago, right, had in mind, because she has drones. So of course they have even smaller batteries and so on. I work with robots that for now roll and walk on the ground. Nonetheless, we pack into them a lot of intelligence, so energy efficiency still comes up, especially for long-term mission. All right. So as Michael said, previously I was at Stanford and I've recently moved to the University of Cambridge. So I will talk about the things that were done first and why this is transitioning at Stanford. I'm just setting up my lab at Cambridge. This is how it looked like at the end of last year. We have some collaborations with people who lend us some hardware, and we're starting to work with humanoids. I'm also getting a few humanoids. There's basically a craze in both the investment and the research world now about humanoids. They're not always the best for everything, and I can argue very well how rolling wheeled robots could be better for many applications. But again, connected to this community, they do need energy efficiency because we want things to be lightweight. So that's one thing. This is how my lab looks like now. We are assembling robots. Our main project is going to be on co-design of hardware and policy learning, and I will talk a bit about this at the end. But as you can see, we're just getting started. So overall, aside from this co-design of hardware and policy learning, we are exploring diverse methods for increasing diversity in reinforcement learning so that it doesn't get stuck in local optima, and I'll talk a little bit about that as well. And lastly, as I mentioned, we're interested in developing resource-aware learning so that you can have robots that are autonomous and that can kind of carry their own energy with them for a while. Right, so before Cambridge, I was an NSF fellow at Stanford, and that was for a number of years, but the last thing that I've done there was take part in the opening of the Stanford Robotics Center. So Stanford brought together basically every department that had anything to do with robotics, and gave them a joint lab space where they could all come together, collaborate on projects, and it's reconfigurable. Also, they can bring in industry. And so the group that I was with took part in basically showcasing what can be done with this. And I will show you some of the demos that came out of this when the Stanford Robotics Center was opened. So overall, just to give an introduction to what I think are the ingredients for efficient robot learning and exploration. First of all, these days we can have scene understanding with vision language models for free, almost. Free in the sense of we don't have to train them from scratch, but they're not free in the sense of that they consume a lot of memory and GPU resources, and obviously they're very resource hungry. Now, once we've done the scene understanding and we know which objects are in the room and roughly kind of what we can parse out from this whole scene environment, we need to actually learn how to interact with this object. So how can we manipulate with these objects? And for this, we need to learn either from demonstrations or from simulation, and I will talk about that. And lastly, so this is the new direction, which I'm going to be exploring a lot in Cambridge now, is that traditionally in robotics, we kind of treated the robot body as fixed. So maybe there was a hardware engineer who designed a robot, and then they iterated on the robot a bit for optimizing its hardware properties, and then they gave the robot to the users or to other researchers. And they iterated on how to learn controllers and policies on this robot. This is a disconnected view. So the vision now is actually to put the hardware optimization in the loop together with optimizing the controllers, or I will call them robot learning policies. So a few years ago, we had this work together with colleagues at Stanford, Google, and Princeton and Columbia on that we call TidyBot. So basically, it's a robot that tidies up your place. It looks for items that are maybe scattered on the floor, and it learns how to sort them into appropriate containers. Now, the main idea here was that not only this robot can pick up items and sort into some predefined containers, but because of its integration with the large vision language model, it can automatically know what items should go into what containers. And not only that, but it also can personalize this to your particular home. So, for example, if you give the robot just a few examples of what should go where, the vision language model can help the robot understand the general category of the object, but also the more specific rules. Like, for example, if you picked up a dark shirt and threw it in a dark hamper, then maybe that dark hamper should house all of the non-white kind of clothing, so things like that. So how did this work overall? We had an overhead image where we are just looking at the scene overall, parsing out the objects in that scene. So this is like just object detection. Then the robot would drive up to one of the objects, and then we would use a vision language model in order to figure out what object it is, figure out which category it is in, and then basically understand what personalized rules should apply to it, given not only the general knowledge that it has about, oh, it goes into recycling bin, the code can, but also the indications that the user had given it. So initially in the lab, we've experimented with just like every lab would do, with particular setups where we would lay out objects on the floor and let the robot sort them out. We also ran some user studies to understand whether people indeed agreed with the choices of the robot, and we got some good results there. But what was good about this is that we could have some kind of dynamic behaviors. We didn't have to care anymore about how to place objects in a very kind of predefined manner. And we could also work with the formable objects because, again, now the large vision language models came to the point where it was easy enough to parse. So with this, you can do something like laundry sorting, which was very, very popular with pretty much everybody who's seen these demos. Furthermore, what we also enjoyed is that the resets for the environment, instead of laying out the objects in a very careful manner, looked more like this, where you could, scatter things around on the floor and keep going. So we got this. We didn't have to train the large vision language model. That now comes with basically its availability because it has been trained by a few of the large companies that make the interface available. But we've integrated it with the robot that pretty much now was enabled to do autonomous kind of cleanup in the house. But as you have seen, as you saw, the actions that it actually did were rather simple, like pick something up, open the drawer, place something in the drawer. So they were not particularly complicated in terms of how you manipulate with the objects. And obviously in robot manipulation, we consider much more advanced tasks that have to do with, actually handling the object. And furthermore, we also want to learn basically these tasks from maybe a few human demonstrations. So if the person shows you how to execute the task, we want the robot to be able to repeat. However, not only repeat that, but also generalize to different orientations that it might kind of approach the object from and different sizes of the object, because we don't only want it to be able to deal with exactly that object on which the demonstration was done. And for this, we had a series of work that leveraged equivariance. So basically, the idea here is that when a human is confronted with the task, they think about kind of generally what are conceptually the actions that should be applied to the object. And then they can actually generalize their motions, not to exact kind of manipulation with the object, but conceptually what should be done with the object, and then adapt what happens to their body to this kind of conceptual understanding of the task. Robots cannot do that yet. So this is what we wanted to do here, where we would build in the equivariance in the sense that we would scale up the actions and rotate and translate the actions if we have detected that the object itself has changed by scaling, rotation, and translation. So the way that this works is that we would build in the equivariance basically into the neural network architectures that were used during the policy learning. And so as the result, what would happen is that if the source object was rotated, translated, and scaled, we would get the output actions also rotated, translated, and scaled accordingly. Now, this is a soft way of doing it. So you still have all of the neural net kind of learning logic that is in between of all these. So in a sense, this was helping to prime the network, the policy learning network, to scale, but it didn't really hard code exactly the scaling and rotation. So that's generally how it works. And with this, what we were able to do is demonstrate on source objects that were just tabletop, small, like handkerchief or small dots, and then have the robot generalize to perform the actions on much larger versions of this object in a zero-shot manner. And by zero-shot manner, I mean that you train the policy on these human demonstrations, and then you run it directly without any retraining on these robots. So we're operating in the end effector or task space, or Cartesian space it is also called, where basically we're here tracking the fingers or finger motion, recording what happened with that finger motion, using learning from demonstration methods in order to train the policy, and then transferring that motion to the motion of the end effectors of the road.
What's the representation of that policy? Like, for example, for this box closing, in what form is it represented? As vectors, you would say, or?
Right. So this policy we've started with, and I'll talk a little bit more about this. We started with this policy basically is just a neural network that runs behavior. Behavior cloning is a particular, let's say, default and simple method for kind of copying over the motion. And now I will talk about the actual parameterization that works for it when you want to execute complex tasks. So currently, the state-of-the-art learning from demonstration, let's say, approach is using diffusion diffusion policies for learning from demonstration. And so basically the way that this works is that there is a diffusion process that that starts with basically, let's say, the motions looking at random noise, and then denoises that to the motion that it has observed during the actual demonstration. The benefit,
dimensions, the Cartesian space?
The output dimensions are Cartesian space of the end effectors.
And the pose.
And then
and their pose.
Pose orientation.
Yeah.
So that includes the Cartesian space. And this is time dependent, right? So it actually, the diffusion policy outputs a sequence of actions. So you can start executing them and it will output like however many you want, 8, 16, whatever. And then as you're executing this first few actions, you can query for the next, with your current state for the next sequence of actions and so on. So this thing is pretty beefy and, takes some time to do the inference. But with this sort of, because it outputs a sequence, you can actually start executing already and you can get reasonably high frequency. Right. So the reason why diffusion policy here is useful is because it can handle multimodality. So if somebody demonstrated doing a task in multiple different ways, behavior cloning would just find some sort of a mean and die. But diffusion policy can handle multimodality, and so it will be able to kind of recover from this and maybe pick the dominant kind of mode and handle that. Now, it's not as simple to add equivariance within the diffusion process. It's still neural net architectures down the road, but when adding that, one has to ensure both that you have the equivariance in a valid way and that the result is an actual valid diffusion process still. So this is what we've done here. We've shown that the result is still valid, and then we have demonstrated with just a real-world experiment how this would work. So for example, here's a person closing a luggage, and then the robot closes a larger luggage, again, without retraining. Now, this is a fairly simple task. A slightly more difficult task is, for example, covering the bed. So the person is demonstrating how to unfold the towel or cover with a small towel, and then we're transferring this motion to the robots. Now, this is not the only way, of course, to transfer the motion. You could, for example, let's say, do some sort of augmentations where you would try with some computer vision techniques to rescale and rotate your representations, and then try to execute that policy. But as you can see, this diffusion policy with augmentation usually doesn't work so well. And actually adding this equivariance is much more robust. Now, every now and then it would get 20, 30, 40, 68% success rate, but across the board, we see that we get a much better result.
Can I ask a dumb question here? So the human is demonstrating this folding action, but how do you detect that this grip has to be executed and it must grab the fabric?
So
basic stuff like that.
Yes. Luckily, we have the computer vision community, and they have a whole subfield of parsing human hands, tracking human hands, understanding whether something is grasped or ungrasped. The only thing is that even though they're far along, you can see that the motion of this person are not very natural. It's like kind of trying to show, I have pinched this, and now I am folding this.
So you trained, or you got a pinch detector?
Yeah, so this now, it used to be detectors that every roboticist would have to train. Now what you can do is you can go and pick up a computer vision method off the shelf that would do this for you. So there are segmentation methods, there are hand tracking methods, and so on and so forth.
Okay.
So all we would have to do is something very simple, like if we wanted to detect grasping and we weren't satisfied with some off-the-shelf detectors, we would have to do that, but we wouldn't have to develop the whole pipeline for example, hand tracking.
Or are we specialized to this particular task of making the bed?
No, not specialized. That is just very general. So yes, so the reason why we didn't bother making this look much better is because this is a totally computer vision question. So yeah, even if it's now not perfect, 3 years from now it will all be solved. So
Honest has a question.
there is a lot of work.
Yeah.
there. Yeah.
I was kind of wondering because I still don't quite understand why the policy learning here knows that, for example, you could also interpret this as grab this thing and move it by 20 centimeters, or you could say grab it and unfold the sheet until it is flat and so on. So I'm kind of trying to understand, like, what's the goal that this thing's trying to achieve? Like visual similarity, or is it like internally there's a model of like sheets that can be folded or not folded? Or
I think it's if you're demonstrating kind of like in this task, right? If you're demonstrating something that is conceptually similar, this is what it's trying to achieve. However, so it doesn't have to be exactly the same trajectory, but it has to be the task that is, for example, you want to cover the box. Okay, now you can cover boxes of all shapes, you know, and aspect ratios. You want to close the box. Okay, we can't really generalize to closing a completely different box, but any box with 3 flaps, we can close. So things like that, right?
But is your instruction textual? You say the box must be closed through an LLM?
You can do that. Not interested. I am not interested in this aspect. So you can definitely do that. And many of the demos right now would give you magic. Text input, robot output. You can do this. So again, this part, there's some things that we're not looking at because they're solved in other communities, like whoever trains the VLM can do that. What they cannot do is they cannot necessarily have the robot move in a predictable and useful manner. And so this is what they focus. But you can do that.
Why do all the robots seem to just drop the thing at the end? Is that just because of the view? So like almost all the robots at the end of their task,
They're
just
letting
complete it
go.
by going.
Oh yeah, they're just letting go at the end.
Yeah, but
Yeah.
that's not copying what the person's doing, or is that just
For
hard to do
covering?
because it's like a
Yeah,
top-down view? Because
I
like
guess.
robots to close
The
the
only
box.
thing is that, so this is a little bit sped up, right? So there might be some frame droppings. Let's see, we will see more videos
Eventually,
of this bad sheet and you will see what we're doing. But yeah. Right, and see, these are some of the other tasks that we've worked with. And so basically, the idea is the same. If you have a different view from a different perspective, or if you have different aspect ratio resizing, now you can do that with zero retraining. Right, so you noticed that I said that we're transferring the motion from what the human hands are doing to just the end effectors. But what happens with the whole control of the robot? And so this is recent work that we've done with colleagues at Stanford, where, of course, whole body control has been explored in robotics for a while. But what was missing really is an open source and open hardware platform to do this in a very simple manner. So basically, now we have a way of doing whole body control where we are not only worrying about what happens instantaneously with the robot, but also how can it do a more long horizon tasks. So for example, here we have some of the noise. We have some way of doing long range reasoning. For example, you drive up to this cupboard, and this is actually kind of like a long range action. And also a way to reason about what do you do after you drive up to this, let's say, cupboard. You want to get something out of it. You want to do fine manipulation with an object, like, for example, get a remote from inside of the drawer. And so now with this policy architecture, what we can do is we can train policies that are long horizon, and they can not only just follow instantaneous, like what to do with the object, but also navigate around the room and still be very, very efficient, and not interpret that as a sequence of many minute kind of motions if you're just doing kind of like a longer horizon, large scale motion. And all of this is integrated into a whole body controller where we have this hardware platform. So it's open hardware in the sense that there is a website where you can go and you can figure out where to purchase all of these parts. You can put them together, and we've reproduced that in my lab of Cambridge as well.
And what's the build cost?
The what?
Build cost. Yeah, what's the cost?
$4,000.
12,000. Okay.
4,000.
4,000.
Yeah. The thing that we're most proud of in this platform is that it is fully holonomic. So this robot can roll around. It's not like a car. It's an actual thing that can, that has a free range motion on the plane of the floor. And because of this, I mean, this is a slightly larger version. I built a smaller version in my lab. Because of this, it's somewhat maneuverable and decently low cost. And the other thing is that it is very accessible. You can put that together even without any soldering. So there are parts available out there that you can put together in darkness.
What does the person hold in their hand?
Yes. So this is an interface for using either your iPhone. I don't think we yet have an Android interface, which is in a mission. I should do this. She's holding her iPhone and she's demonstrating to the robot how to do the task. So this is like an interface for collecting demonstrations. Right. Yes, and and there's an interface there for go forward. So other than putting together this 4K robot, you don't need any special equipment. This arm itself is a bit expensive. The one I have in my lab is $2,500, so that's easy, and you can put any on that. Right. The other thing that you could do is you could take pre-trained policies that you've already had, and there are many that have been trained by other roboticists in the community. And if they're static, so for example, somebody trained a policy just to do something on the table, you can mobilize them. So this is the idea of Mobify that we've just finished a few weeks ago, where we can figure out how to do the long-range navigation for you. And then we can basically drive up to the place that is in distribution as the starting position for your pre-trained policy that you have trained before. And so with this, basically, you can use the policies that are already working, but if something changes in terms of the overall kind of navigation plan, we can use simulation and a bit of also computer vision with Gaussian splatting in order to understand how to move around the environment and then drive up to the place where you can start executing. So this is all kind of going towards letting you, in the previous works, collect demos and train policies that are somewhat generalizable from a few demos. And in this work, mobilizing the policies that you already have so that you don't have to continuously recollect the data if something changes in your overall layout. All right, so now learning from demonstration is very popular these days in robotics because you can actually get stuff working. But what I'm most interested in is for robots to actually learn autonomously. So I'm most excited.
Can I just interrupt? You say learning from demonstration is very popular because you can get things to just work. But all you showed here is a lot of RL in simulation world, right?
Previously, no RL.
Oh, so all these simulated kitchens and so on were not, well, that was not RL stuff?
No RL, yeah, just a simulation, and then you drive robot around. It's like a sampling or an optimization. No RL. No RL.
I see.
Yeah. Now we're going to go to.
Okay.
Yes.
One more question. So there is no LLM either here. It's not like there is a visual model that understands what human is doing, translates that to LLM, and that's not like that.
No LLM.
Just directly from the.
Yeah, because basically what the LLMs are really good for now is this segmentation and high-level understanding. But if you're trying to twist a deformable object, or if you're trying to unlock something, it's still difficult for them to figure out what it is that you're trying to do. They don't know anything about forces. So until we train a foundation model with forces, then it's really difficult for them. And even if we train it with forces, it is harder to generalize from force information than from images, both because of how they are sensed. So there are different kind of ranges of forces that different hardware can execute, and also just precision of sense. Yeah. Right. So I would like to have RL in this whole pipeline. But without simulation, it is very difficult to do it. The only thing that these days succeeds with RL without simulation is quadruped locomotion. Maybe a bit of humanoid locomotion, but not as much. But quadruped locomotion is basically solved. You can just do RL on hardware done without any simulation. In manipulation, this does not work. And even RL in simulation for manipulation is still pretty challenging. But even to start thinking about it, we need to understand how to have simulators that are aligned with reality, so that when we train with RL or with anything else in simulation, this actually has relevance to what happens in reality. So for this, I've looked at two directions. One of them is differentiable simulation. So this is very easy to explain to people in the academic community, because basically there is a way to treat a simulator as just a function through which we can propagate the gradients. The way that this is done is that there is a program that is modified or written in such a way that you can propagate the gradients. It's not a neural network that is trained from data. It's your physics rules that are encoded And then they're written in such a way that you actually kind of can propagate the gradient through them. So these are special programs. And what you can do with them is you can do reality to simulation alignment by inferring the physics parameters, because you can directly propagate the gradients and choose or align, like adjust the physics parameters if you are able to propagate the difference between the reality and the simulation output. You can adjust the policy directly as well in a similar manner, and you can even adjust geometry or other parameters so you can get morphology optimization and change the shape of the robot. So this framework is very popular. It's kind of like, it seems like it has a lot of power, but it also has a few challenges. So inferring physics parameters, what you can do, for example, is you can start with some piece of, roughly modeled clothing. Here it's basically modeled with different bending and elastic stiffness in different parts of the clothing. And in a few episodes, you can align it with what you have in reality, either from tracking the corners, or we've also done it from collecting the point cloud and aligning directly through matching the point clouds simulation from simulation.
The properties of this simulated material with the
Yes.
real material.
Exactly, simulated material with the real material. And the other thing that you can do is you can get the policy parameters that are optimized. So here, just in simulation, you can directly propagate the gradients for the motion of the sladle and figure out how to make it move such that it picks up this sugar cube, for example. So this sounds great because it seems like it's a shortcut for everything, right? You just propagate gradients and you're done. But if you actually look at the optimization landscapes, you will see that it's not something that a single gradient descent can handle. So here is, for example, the 2D slides of the high dimensional landscapes, and you can see that there are many local minima. So, if you just start your gradient descent in an unlucky place, you're not going to get to the global minimum. Worse, there are many instabilities along the way where things are barely differentiable, or in practice not differentiable, unstable, and you have not a number, or infinities or some other kind of results of instability. Even if you don't have these issues, and if you're working, for example, this is plastic deformation, so your optimization landscapes come out as very, very smooth, what you will be battling with are the plateaus, where you will get stuck on a very kind of flat plateau, and it will take a very, very long time to progress to some sort of an optimum. And if you have interactions on the interface between rigid and deformable objects, then you would have this seemingly high frequency noise, but you can't really remove this with traditional signal processing techniques. It's not high frequency enough. So you have kind of very sharp local minima from which it's very, very hard to get at as well. So you would think that maybe there's a way to sort of decompose and get to the bottom of it, of what is the problem. And this is the thing that we tried to do in this work from a few years ago that was presented at Conference on Robot Learning, where we tried to understand, okay, if we just look at something very simple, just interactions between a rigid ball and a few rigid colliders, what kind of problems would arise? And so we can see here both the plateaus and also these sharp kind of differences in values on the landscape when there is a contact. And so basically the problem here is that you can smooth a little bit, you can adjust a little bit, but fundamentally the problem of contact-rich interaction is not going to go away, and you're not going to have very easy way propagating gradients through landscapes like this. So one of the ways to solve it is to combine gradient-based techniques with gradient-free techniques and population-based sampling. So what we proposed in that work was to combine global optimization, in that case, Bayesian optimization, with semi-local optimization, which was things that are similar to CMAS, and with the gradient propagation in simulation. And so with this, you can actually succeed in descending on these rough landscapes without having to kind of smooth them, without having to play any kind of task-specific tricks. So this is very general. But of course, there are challenges that remain. So one, it doesn't succeed on everything. The instabilities, if you have a lot of them, they still will, come back to haunt you. And the other problem that you have is that actually differentiable simulators are programs that you have to write. So it's not like any generic program that somebody had already written, can be in 5 minutes be made in a differentiable simulator. So many people are still using non-differentiable simulators. They have been a lot developed in the community. And so the other line of work that I've done is how to align non-differentiable simulators with reality so that you can then do RL in them, and that gives you a policy that transfers to real robots. And for this, I've explored something that relates to distribution embeddings. So I will talk about this a bit. So this is our hardware setup here. We're just working with the formables, and we're trying to wind this rope around the pole there. The task here doesn't matter. The only thing that matters is that we're trying to understand what is happening with the deformable object and how we can align the properties of this deformable object from simulation to reality, changing its bending stiffness, elastic stiffness, friction, and scale parameters. So the method proceeds as follows. We sample simulation parameters from some sort of a prior, can be completely uninformed, and we create simulated trajectories. Then we extract key points that roughly keep track of the motion of this deformable. So this is, again, we go to our computer vision friends. There are many key point extraction methods, and this is fairly easy to do and fairly fast. But the problem with them is that they would jump around on the object. So they basically would reorder themselves. They would come in and disappear depending on the occlusions. So if you try to basically use this as a representation that you would put into, let's say, a neural net that trains to do something, it's not going to work very well. And so what we've done here is we've developed what we call here an ArcHSNet layer, which embeds this key point representation into a higher dimensional space. And I will explain how it does this, but what it accomplishes is it gives us permutation and variance, robustness to noise. We also get a convenient distance metric, so we can actually compare the states of the object in this way in the principled manner, and some nice continuity properties. So if you hear the word embedding, then you probably kind of already have in mind some embeddings that you're familiar with. And here in this particular case, we've found a way to do this with random Fourier features. But we've done it in such a way that the parameters of these RFFs, random Fourier features, are adaptable. And so overall framework basically allows us to keep this network layer as completely differentiable. And so we put in this random Fourier feature representation as a differentiable and adaptable representation that can be incorporated into any pipeline. So the idea here is that we will approximate this embedding using the samples. Our samples in this case are the key points that are just outputs of this, tracking method that we use. And then we use the theory that comes from a song from 2013 on kernel min embeddings that basically talks about how to interpret basically how to get the distribution embedding that in a non-parametric way represents these points as a probability distribution of the, let's say, in our particular case, underlying shape of the object. So effectively, instead of looking at them as just points in space that represent some key points, we're interpreting them as samples from a probability distribution of the shape of the object. So we're uncertain about the shape of the object, but these are our samples, this is our evidence. And so with that, what we can do is we can take these key points and extract the random Fourier features from that. You can use different representations here. It doesn't have to be random Fourier features. Any feature extraction method that you like to use within your kernels can be used here. And what we can then do with this is that we can have the adjustable parameters of these random Fourier features set up in such a way that they are differentiable. So this becomes a differentiable neural network layer. Effectively, what we're doing here is we are projecting onto the axis in a much higher dimensional space, where the dimensions now are the functions, and the functions are the sine and cosine functions, or any functions that you're going to be using if you're using a different way of doing feature extraction.
Why do you pick Fourier space? It's a bit weird, this periodic space for these key points. Why do you choose this Fourier? Things with phase and interference and stuff like that. How did you happen to come to that?
Right. So there are a few reasons. One is they basically mostly lose their interpretation of being periodic here. So the periodicity kind of doesn't really come into the play so much so. There's a little bit of that left if you're trying to see something on a like high frequency versus not, but it's very subtle. The main reason for using RFFs is that they have proven to be the most robust, and let's say you don't need a very high dimensional RFF in order to capture a lot of detail. And we have tested this in other works that we're doing with Boston learning and also in this.
So each 2D key point is then represented by a bunch of Fourier phases,
Yes.
amplitudes,
Yes.
and that's it, right?
Yes,
And frequency
yes,
and,
Yes.
and angle, yes.
yes, yes.
How, like a 10-dimensional vector or 100-dimensional or,
From 40 to 200.
okay.
Yeah.
So
So-
2D is like 40 to 100 dimensional.
Yeah. And in the machine learning world, this is actually perfectly fine and even desirable. So I have shown that, for example, if you, for a low dimensional representation that is difficult for RL to learn, for example, expand it with RFFs, RL has an easier time learning. So
Why
it's
is
almost
that?
like,
Why is it easier?
why is it easier? It's because you're sort of giving it, it's a little bit like, for example, currently in LLMs, there is this notion of encoding the location. And yes, exactly. So, you would think that just encoding the location with the minimal number of dimensions would be optimal. But actually, neural nets first have to sort of
Using a
expand
population
it,
code.
yeah,
Using a population.
to
code.
understand what to do with it, learn these weights, and then continue going, right?
Okay.
So this expansion here happens automatically, and it seems to be a robust enough representation that it doesn't lose information and is nice. And specifically, the doesn't lose information part, I can go into more detail. There's a bit of math here, but what comes from this this work is that there is a way to leverage the theory of distribution embedding in a way that is kind of lossless, right? So all of the information that was encoded in the samples is retained for when you're using this.
Well, I mean, there's always noise and stuff, and Joel Burdick, when he was here, spoke a lot about the fact that real sensors have really a lot of noise.
After you sample.
After you
After
say,
you
yeah.
sample.
Anyways, the
Yeah.
question from right here.
Was it inspired by sirens by any chance? The 3D 40 where the people used for nerves at the early days?
No,
No,
but they definitely can
It's-
have some
yeah.
connections, but not really.
but it
inspired.
kind of looks as well like a grid cells in there.
So
Same kind of same in the sirens and all these nerves was this notion of like the grid cells use this sinusoids and we can use them for the
So you
spatial.
use any feature extraction method here. So the distribution embedding basically says, okay, I will take care of representing these points and interpret it, and you plug it into this framework, and I will give you a way to then represent it and samples from distribution. But how you extract features from it is totally up to you.
But it seems to the cosine side works the best.
Huh?
These features.
Practice, right? But as I said, this can be anything. You can create your own wonderful feature extractor, and as long as it has some nice properties that still maintain the final properties of the distribution embedding results that you have from theory, then you're all good. Right? Yeah.
Have you noticed that, but for you, that the frequency space, that if you use random frequency space, it works better than the integer space?
So we adjust frequencies, right? So both.
You learn them.
Yeah,
You learn-
exactly.
Okay.
Exactly. So sometimes, and I kind of debug this to see whether something interesting is happening there. For a few tasks, you do have a shift in the values, and they're quite different from what you started with. But for many tasks, actually, they remain very similar to what it was before, which means that if you just use that's good to find. Right. So why did we do all of this stuff? The reason why we did this is because we wanted to see how to have a neural net layer that can give us this nice representation that can let us run inference methods in order to infer the simulation parameters. So here, what we can do is we can train an inference method that is pretty much off the shelf. And then with just a fully differentiable neural net, have a way to align between the simulation and reality. So in reality, we do one sample, compare that to the outputs of the simulation that we have so far, propagate the difference back, and then resample again and keep on going. So the difference between having the representation that is just key points, which doesn't decrease the distance to ground truth, to the representation that we have that has a fairly rapid drop in the distance to ground truth, showed us that, okay, that's great. We now have a representation which is fairly good for deformables. And so we have considered a few of these tasks. Here, the task itself doesn't matter. It's like some wiping or some stretching a tire onto the poles or unfolding the fabric. But the main idea is we wanted to see whether we can kind of adjust the properties of different kinds of deformables, like highly deformable fabrics, 2D deformables, 3D deformables, and align objects like carbon. All right, so now I'll come to the last part here. And we have a way now, let's say, to learn from demonstrations or to train in simulation. And now we can use off-the-shelf RL methods on the simulators and then transfer from simulation to reality because we have aligned our simulator. But ultimately, this is all still for a fixed embodiment. So if a robot can do a certain thing, it may be able to learn to do that. But if it is physically impossible for the robot to do that, then we're out of luck. Or if its embodiment is such that it is very difficult to learn, like, for example, it doesn't have the right sensors to really progress with learning very easily, then this is also a problem. And so because of this, in my next stage, at least for the next 4 years, I'm looking very deeply into how to adapt the hardware and how to do this together with adjusting the pose. So previously, we've had a bit of work showing how to optimize morphology, again, with differentiable simulators. So this is the last part here where you can propagate the gradients, but now actually optimize the geometry. So there was work from MIT called DiffHand that looked at it, and there were previous works as well on this topic. But they have leveraged the technique from computer vision that has been around for quite some time that's called cage-based deformation. So what you can do is, instead of adjusting every single little point on your mesh, and this mesh might have tens of thousands of vertices, you can pick a few kind of dominant vertices, and then when you stretch them, you don't completely and weirdly deform the object, but you can still keep some kind of nice properties of this object as you deform this cage. But the work that was done before was looking at tasks like, for example, find out how to change the shape of the arm or shape of the finger in order to reach a target. And this you can very easily do with differentiable simulation because the optimization landscapes are fairly smooth. You're working in free space, and so this is very nice. The other part of the work showed how to touch like an object in one point or something like this. Again, this could still be tractable. What we looked at was something like winding the rope on a tool, where you have a lot of interactions between the tool and the rope. And then if you look at the optimization landscapes that come out of this, and you take like a 2D slice, for example, then you again are back to the setting where we were before with a lot of spikes and a lot of noise. So in this particular case, we decided to leverage some of the structure that we have here with the cage-based deformation and bring in also some techniques from continual learning. So we said, okay, we will optimize a subset of parameters of the cage at each time, and we will aggregate the knowledge by basically first learning from a simplified, let's say, subset of task variations, and then expanding that task variation set, but also doing it in such a way that we make sure not to forget the information that was learned from the previous batch of variations. And so with this, we were able to automatically adjust the shape of tools. So for example, if you start with some blob and you are trying to push this irregular shaped bead onto some sort of a receptacle, then you can automatically come up with a shape that is curved. And this actually winding tool, similarly, we started with a block, and then the optimization automatically found for us this shape, which has the extended ends of it. As a human,
what's the difference? What's the difference between the naive tool? It's too fast for me to follow.
Oh, there is no naive tool here visualized. It's just a block. Here we're just visualizing the resulting final result of the optimization. So basically, what we've done is that we ran the optimization and then we 3D printed the final result. So this.
You mean this blue thing?
This blue.
Oh, I see. Okay.
So more than anything else, this was a proof of concept. So basically saying, okay, well, you can do this with differentiable simulation, even if you're working with somewhat context-rich tasks. I will take this on and develop this further. I will show you what we're trying to do in Cambridge now. But we also kind of face some problems along the way. And so I think what we've kind of preliminarily explored here of how to kind of decompose this into a sequence of optimization steps and bring in continual learning will help us later on. Right, and finally, so this is about kind of optimizing the shape of your robot, that's right, but your robot also needs sensing. And so the last thing that I've done before leaving Stanford was collaborate with colleagues from Mark Kosti's group that developed a lot of different interesting sensors. So this is, for example, a force sensor that can sense not only the normal but shear force. So this is fairly rare, and it's also very cheap. So it's like $10 to $20 once you set it up. And it also has a flexible PCB, so you can actually wrap it around. So these are sensor arrays, basically, that can be expanded and wrapped around an arm or some.
How big is that thing there? I'm trying to get some idea.
How big is this thing?
See, there's a Hall sensor?
Here. Yeah.
Okay.
So here, there is a magnet, a silicon. The silicon, the thickness of the silicon changes how sensitive the sensor is. And then each of these taxels basically is a sensor. And so you can have more of them. And
so as you press on the silicone, the magnet moves closer to those Hall sensors or something. What are those? Yeah, Hall sensors.
Yeah. And then you basically change. You're basically sensing the change in the movement.
I see.
Right. And the other good thing about it is that it also is. It can sense. It can collect data from all of the taxels. So simultaneously, so it's not like one press. So what we've shown is, for example, is that it can help in balancing. So if you put this food container on top of the robot, then the robot can balance the food container, and it is also nicely reactive. So for example, when I pick up this food container, the robot knows to go to a different state, knowing that, okay, the food container has been retrieved. All right, so I mentioned the Stanford Robotics Center at the beginning, and that was because we put it not all together, but we put some of these pieces together and show the more robust demos to thousands of visitors that came to the opening. So the opening was kind of like a week-long thing where at the beginning there was some interviews with the press. And then for the opening weekend itself, there were visitors coming from the community, from companies, from research institutions from across the world. And this was kind of one of the first things that I had outside of industry, where we took the research prototype and we actually built something that had to work continuously for the whole week. This doesn't normally happen. It took a lot of work, and now I'm inspired to try to kind of maintain this kind of level of readiness for demos in my time at Cambridge. I'll play a few of these just for you to see what was recorded with the date, and then we will go on to the last part. Maybe I won't play it. Never mind. All right. Anyways, without the noise, you can see the robots. But yes, as you can see, they're dropping, so they're not like covering maybe the way the human would cover the bed. The thing that we liked about the demonstrations that were developed, the reporters got excited because usually when the reporters come to film the labs, they're told where to stand and what to touch and what not to touch and how to breathe, right? Because, things are pretty fragile. But here they got to like throw clothing anywhere. The robot can go and pick it up anywhere. They, would throw the balls, and then the robot would throw them back into the container. And so they kind of felt that it was much more fun to report on because this is something that it actually, is somewhat robust. And this reporter asked us whether the robots can cover her while she's lying in bed. It is very natural for a human to come up with this, but we have not actually ever tested this with a human lying in bed. So we were not sure what exactly would happen. And the highlight was at the end, she asked us to turn off the lights. So this still worked and nothing, went haywire. But it was kind of, a big inspiration for, okay, now finally we're at the stage where our hardware, software pipelines are built up to the point where we can entertain the reporters and also the visitors. All right. So to mention a bit more about what we're doing now at Cambridge. So I mentioned this co-design of hardware and policy learning. This is a 4-year project that is funded by the new funding agency called ARIA. They're very fast moving. They're very, very supportive of both fundamental research, but also figuring out how to make these things work. So very excited to work with them. So the idea here is that we want to view the kind of optimization space as a joint space between what can be changed with the hardware design and what can be learned from a policy. And so with this, we can do things like this inspirational example from a group at Stanford that collaborated with, that's led by Monroe Kennedy, where they have attached a fingernail, as you can see there. I will use my mouse. Attached a fingernail and enabled this hand to pick up very thin objects, like, for example, a coin from the table. So this is normally very difficult, but this was kind of a back and forth between a human kind of reshaping this and a little bit of optimization going on. We want to do something like this completely autonomously. So we will consider morphology changes, actuation changes to some extent, right? We're not building completely new actuators, but change some of their properties, changing materials, changing sensor placement, but at the same time, also searching the space of reinforcement learning policies, because there are some policies that can leverage very noisy inputs. There are some policies that actually prefer lower dimensional, cleaner input, and so on, right? And so basically finding for a given a set or suite of tasks the optimum that has both a good low-cost hardware design and a fast enough and robust enough learning method, that is what we're basically aiming for. And there are many kind of research sub-questions here, and so that's why it's a 4-year project with a sizable part of my team. A part of this would definitely be using extensive real sim alignment, because we actually want to do this hardware optimization in the loop, so we don't want to do just optimize the stuff in simulation and then find out that, okay, it doesn't work in reality. We want to continuously be learning in simulation, but also continuously aligning the simulation with reality. And starting with some of the open source hardware that other people built at CMU, for example, figuring out how to make it modular so we can make changes without completely disassembling the whole hand here, and exploring this hardware design space online. Now, in terms of the co-design, I previously have not worked in computer architecture, but my department has a very strong computer architecture team, and a subset of the team, like Rob Mullins and Tim Jones, now are a part of this larger effort that is looking at the simulation and co-design for AI accelerators. So here, this is a part of another ARIA project that basically looks for developing next generation AI hardware. I think a few neuromorphic projects are also part of this. And while this team in particular is not necessarily looking at neuromorphics, we are looking at how to create simulations to support whatever novel hardware designs are there, but specifically for AI accelerators. So that's the foray into the computer architecture. And finally, one of the things that I've been trying to pursue for a long time is to how to make RL more effective in learning. So RL is effectively a local optimizer, maybe semi-local optimizer, but it is very visible in manipulation, because you get stuck with this, contact-rich scenarios. You get stuck in local optima a lot. So the point here is that we can actually use distribution embeddings, not just for representing, let's say, the shape of the deformable object, but we can step back and we can use distribution embeddings for representing stochastic reinforcement learning policy. Now you have to think a little bit about how exactly you would do that, but there is a way of doing this. And once you've done this, what you do is you get, because of the properties of distribution embeddings, you get a very nice way of getting an estimate of how far the two probability distributions are. So how different two reinforcement learning policies are. And once you know how different they are, you can play various kind of either tricks or find various principled approaches about how to find a set of policies that are somehow spanning the set of policies, or that are maybe independent of each other or different enough. And so we've had the foray into this, not connected to reinforcement learning, but more about learning independent relations with Max, who is actually sitting over there. And we've developed a fairly principled framework of how to do this. And I think it is possible to adapt this framework to something that would work with distribution embeddings that are representing reinforcement learning policies. And so this, I think, I'm pretty excited about taking this to basically make the, combine reinforcement learning with more global optimization techniques in a principled way, and to basically rescue reinforcement learning from being just a simple local optimizer. And finally, a bit more connected to maybe what is relevant to this community is we're starting a few projects on resource-aware learning. So the big problem that we have now, you notice that I brought up LLMs a few times, right? They're very popular in robot learning now for parsing things, for taking language instructions. So they're used almost ubiquitously now in research, and they will soon start to get deployed in practice as well. Now, the problem with them is that if you just naively use them, you would get a fairly low frequency actions, which were not used in robotics to like 2 to 5 hertz kind of controllers. That's too low frequency. The LLMs have really high power consumption, both for inference and for training is particularly bad. And if you somehow combine this with autonomous learning with RL, for example, RL algorithms in general don't really have, they don't natively model device constraints.
Not, they're part of the physics model that is used for training RL, right? Why do
Part
they
of
not
the
model?
physics, so it's just like in the algorithm itself, in the optimization method, there are very few methods that would say like, oh, I have this and this many bits of memory, I have this and this much time, find the best solution for
Oh,
these
okay.
constraints.
I
They
see.
are more like,
Source, yeah.
yeah, exactly.
Yeah.
So what we want to do is we want to have a heterogeneous cross-device inference and learning. And so what this means is that we are going to aim for high-frequency controllers, like what is standard is 100 hertz to 1 kilohertz for like nice robot arms. But we also want to work with VLMs, vision language models. So we will distill them for local inference. This has already been done, quite frequently, but we need to push more on this, especially for vision language models, not just for LLMs, not just for language models. And we need to be smart about having different kinds of hardware that is optimized for different things. So some is high memory and maybe are doing things at the lower frequency. Some is high frequency, but then also low power consumption. And so basically, this is a bit more on collaborating with people like Rob Mullins and the computer architecture group, which will kind of give us some of the samples of the chips that we can use that are specialized and good for one particular purpose versus the other. And on our side, we're working on developing resource-aware reinforcement learning methods that basically, from the start, take the resource requirements and then find the best policy for these resource requirements, as opposed to just post-fact and being cut off by resource.
At least the RL control methods I'm aware of, like for quadrupedal walking, they define the neural network architecture up front. And in the end, all these trillions and trillions of cycles are just training a few 100,000 weights in this small neural network.
Yes, exactly.
The neural network is basically zero cost compared to everything else.
But
these RL walking robots, like in Hooter's lab, and that I know of the best.
exactly.
There's nothing to the neural network. I mean, it's
Exactly.
the tiniest little MLP.
Exactly. And this is the biggest difference between quadruped locomotion and manipulation. I can train quadruped locomotion online from real data where I have 2-layer, 3-layer neural network with 8 to 32
Units for like,
units.
yeah. But
And
manipulation is not
No.
much bigger.
Much harder. And this is because quadruped, especially with like point feet, these are point contacts, and these are the hardest parts. And you only have 4 of them, and they're somewhat periodic. So that is the biggest difference. So like that neural net can cope with that. And yes, if you have some sort of rich, really challenging terrain, you would need a little bit more than that, but you still can do it. And you can still do it from scratch and online.
But the
from real data.
things, you have or just pinch fingers. There's nothing to them. They're not fancy hands with all kinds of sensors all over them. They might just be a gripper with one contact sensor, right?
Terms of contact.
But the objects, the way they contact the objects, that generates a lot of contacts. Yeah.
See, so you need much bigger networks to infer.
And the problem is that neural nets are not natively good with discontinuities and sharp kind of transitions. So if there is a network architecture that is good for that, fantastic. Because what happens is in quadruped locomotion, it's mostly the dynamics of the robot. Control people love it. Smooth, right?
Yeah.
Beautiful, right?
Well, it's just continuous, right?
Yeah. It's discontinuous, but only in a few points. And it's somewhat predictable what would happen at that point, because also, well, the object is the ground, that normally doesn't change. And in manipulation, it's mostly completely aperiodic. So you can't bootstrap from learning just from a few seconds because everything recurs after that. Things change. Sometimes objects are deformable, or objects have a lot of hard contacts with what the hand or the arm or the gripper is trying to do. And on top of this, there's a very complicated sequential thing, right? So you can't transition from one part of the task to the next if you haven't completed correctly the first part.
Thank you.
So that's the difficulty. Right. But also because of this, now the kind of things that we want to solve are much more complicated in terms of conceptually, kind of what happens with the scene, what happens sequentially with the task. So we want to use things like VLMs that can tell us who is in the room, what can I do with these objects conceptually, but then we need to put them onto some sort of hardware that can actually manage to do it and not run out of batteries. All right, I think that's it. Yeah, and finally, if there are new hardware architectures that are ready for being tried, even if they're simulated, we're very interested in that as well, of how to incorporate this into this custom framework that has maybe different aspects are good for different things, but maybe if there's some piece of hardware that is, for example, fantastic and low power for a particular application, or maybe there is some architecture that just doesn't get bothered by context and sharp transitions and discontinuities. That would be very well. Right. Yeah, I think we're at time, so